I'd now like to talk about heat capacities. Heat capacities center around this equation, Q equals mc delta T, where Q is the heat transferred into or out of an object, m is the mass of the object, C is the heat capacity, and delta T is the change in temperature. First of all, let me define what heat capacity is. If we take water, for example, water has a heat capacity of 4.18 joules per gram per degree Celsius. What that means is if we have a gram of water and we put in 4.18 joules of energy into that gram of water, it will raise the temperature of that gram of water by 1 degree Celsius. So that's how we get the heat capacity with its units. It's 4.18 joules per gram per degree Celsius. I'd also like to show you a list here of different heat capacities. You can get this out of your book, or you can go on the internet like I did and just find them everywhere. And what you'll notice is that down here, this is sort of in a descending order, heat capacity depends on a couple of things. It tends to be larger for lower atomic weight elements, and it tends to be lower for heavier metals. And there's actually a relationship between heat capacity and atomic weight that we can make use of as well. But you'll also notice that water has a fairly high heat capacity, partly because of its low atomic weight or low molecular weight, and partly because it's a liquid. Alright, let's take a look at a problem that involves heat capacity and temperature changes. So here's an example. What is the final temperature of a 10.00 gram copper ring at 20.0 degrees Celsius that absorbs 45.0 joules of heat? Alright, so what we're going to use is our Q equals mc delta T. We can see that if we rearrange this, we can have the delta T equals Q over mc. And that's what we're doing here. Delta T equals 45.0 joules. That's the amount of heat that was put into the copper ring. The copper ring weighs 10.00 grams, and the heat capacity is 0.385 joules per gram per degree Celsius. So what we find is that amount of energy, 45.0 joules, is enough to change the temperature by 11.7 degrees Celsius. What we've got to figure out is whether that change is going to be a positive change or a negative change, whether it's going to raise the temperature or drop the temperature of the copper ring. Now what we find here is that the copper ring is absorbing 45.0 joules of heat. So whenever I see the word absorbs, I'm thinking that the temperature is going to go up. So the final temperature is going to be 20.0 degrees Celsius plus 11.7 degrees Celsius, which would be 31.7 degrees Celsius. So what's happened in picture form here is that we've got a copper ring and the copper ring has absorbed 45.0 joules. Now initially it's at 20 degrees or 20.0 degrees Celsius, and it also weighs 10 grams or 10.0 grams, and we also know its heat capacity, so we can tell what's going to happen after the 45.0 joules goes into the copper ring. We know that the temperature is going to increase, and that's what we found out when we did the equation here. We found out that the temperature went up by 11.7 degrees Celsius. So you can see all of this is going to be figured out by looking at the wording of the problem. You've got two possibilities here. You can either have the word absorbs or you can have releases. Now if the word here was releases, what we would have done is we would have taken the 20.0 degrees Celsius and then minus 11.7 degrees Celsius. Because what's going to happen is that if it's releasing heat, then the temperature of the copper ring is going to go down, and it's going to go down by exactly the same amount, which is 11.7 degrees Celsius. I guess the important thing for you to remember is that the thing we're measuring here is delta T, which is change in temperature. And whether it goes up or down is going to be dependent on what's happening in the problem. If it's absorbing heat, the temperature goes up. If it's releasing heat, the temperature goes down.